Hello there, and welcome. If you're here right now, maybe you've had a long day. Maybe your mind is still turning over thoughts like stones in a river. Maybe you just want to let go for a while and drift into something bigger than yourself. Whatever brought you here tonight, I'm glad you're here. This is a safe place to rest, a place where you can close your eyes or keep them softly open and just listen. There's no pressure here, no need to remember everything. Just let the words wash over you like gentle waves. Before we begin this journey together, if you enjoy falling asleep to space stories and cosmic mysteries, consider leaving a like on this video. And if you want more nights like this, more gentle voyages through the universe, subscribe to the channel. But no pressure, that button will still be there tomorrow. Right now, just get comfortable. Adjust your pillow, let your shoulders drop, soften your jaw. Take a breath that fills your whole chest, and then let it go slowly, like you're releasing the entire day. Stars are one of the ways God turns darkness into light in his universe. They are distant suns, burning across impossible distances, most of them so far away that their light takes years, centuries, even millennia to reach your eyes. When you look up at the night sky, you're not seeing the universe as it is right now. You're seeing history, you're looking back in time. Some of those stars might already be gone, their light still travelling toward us like a letter from someone who no longer exists. And yet, that light still shines, still tells a story. So let your breathing slow down. Let your thoughts become soft and blurry around the edges. You don't need to hold on to anything right now. Just listen. Just drift. We have 100 quiet truths to explore together, and all the time in the universe. There's nowhere else you need to be, nothing else you need to do. Just rest here, in this moment, as we begin our journey through the life and death of stars. Let's begin. Fact 1. Stars are born in clouds of gas and dust called nebulae. These clouds float in the space between existing stars, cold and dark, sometimes stretching across distances so vast that light takes years to cross from one side to the other. Inside these clouds, the temperature can drop to just a few degrees above absolute zero, the coldest possible temperature in the universe. For millions of years, these clouds drift through space, seemingly empty and lifeless. But they're not empty at all. They're waiting. They're full of hydrogen, the simplest and most common element in the universe, along with traces of helium and tiny grains of dust. These dust grains are incredibly small, smaller than a single particle of smoke, yet they play an important role in what comes next. And under the right conditions, gravity begins to pull parts of these clouds together. Sometimes a nearby star explodes and sends ripples through the cloud. Sometimes two clouds collide in the vastness of space. Whatever the trigger, once gravity takes hold, the process of star formation begins. By the laws God set in motion, the cloud starts to collapse inward, slowly at first, then faster as more material gathers together. Fact 2. Gravity is the invisible hand that shapes the universe. It's the reason planets orbit stars, the reason moons orbit planets, the reason you stay firmly on the ground. And in these nebulae, gravity finds regions where the gas is just a little bit denser than the surrounding cloud. Maybe there's a slight concentration of molecules in one area. Maybe the cloud has been disturbed by some outside force. Whatever the reason, gravity pulls on that denser region, and as material falls inward, the region becomes even denser. This creates a feedback loop. The denser it gets, the stronger gravity pulls and the faster material falls inward. The gas pulls inward from all directions, and as it does, it begins to heat up. This is the first step in creating a star. A clump of gas growing denser and hotter buried deep inside a cosmic cloud. From the outside, you wouldn't see anything special yet. The cloud still looks dark and cold, but inside, change is happening. The seeds of light are being planted in the darkness. Fact 3. As the gas clump continues to collapse under its own gravity, it begins to spin. This happens because of something called conservation of angular momentum. Imagine a figure skater pulling their arms in during a spin and rotating faster. The same thing happens with collapsing gas clouds. As they shrink, they spin faster and faster. The material begins to flatten into a disc shape, with most of the mass concentrated in the center. This spinning disk of gas and dust will eventually become a solar system. The central bulge will become the star, and the outer disk will form planets, asteroids, and comets. But right now, at the center of it all, something remarkable is beginning to happen. The core is getting hot. As particles crash into each other, their energy converts into heat. The temperature climbs higher and higher. The pressure increases as more material piles on top, and deep in the center, hidden from view, a protostar is forming. Fact 4. Temperature is really just a measure of how fast particles are moving. When gas particles collide and compress, they move faster, and the temperature rises. In the center of this collapsing cloud, the core temperature climbs higher and higher. 1,000 degrees, 10,000 degrees, 100,000 degrees. The pressure becomes immense, crushing the hydrogen atoms together with tremendous force. At these temperatures, atoms start to break apart. Electrons are stripped away from their nuclei, creating a state of matter called plasma. The core glows with invisible heat, though it's still shrouded by thick layers of dust and gas. And when the core temperature reaches about 10 million degrees Celsius, something magical happens. Hydrogen atoms begin to fuse together, they combine to form helium, and in that process they release energy, enormous amounts of energy. This is nuclear fusion, the same process that powers hydrogen bombs, but happening in a controlled, stable way. And when fusion begins, a star is born. Light erupts from the core, pushing outward against the crushing weight of gravity. Fact 5. The moment fusion ignites in the core, the star pushes back against gravity for the first time. All that energy radiating outward creates pressure that opposes the inward crush of gravity. The two forces reach a balance and the star stops collapsing. It settles into a stable state that it will maintain for millions or even billions of years. This balance between gravity pulling inward and fusion pressure pushing outward is what defines a star's life. It's a constant tug of war, a cosmic battle fought every second of every day. As long as the star has fuel to burn, the battle stays even. The star shines steadily, neither growing nor shrinking, but gravity is patient. It will wait as long as it needs to, and one day, when the fuel runs out, gravity will have its victory. For now, though, the star has found equilibrium. It has joined the cosmic dance, taking its place among billions of other stars scattered across the galaxy. Fact 6. Not every collapsing gas cloud becomes a star. If the clump doesn't gather enough mass, it will never get hot enough in the core to start fusion. These failed stars are called brown dwarfs. They're bigger than planets, but smaller than stars, glowing dimly with leftover heat from their formation but never truly igniting. They drift through space like cosmic embers, warm but not burning, hovering in the twilight between planet and star. To become a true star, a gas clump needs to gather at least about 8% of the Sun's mass. That's still roughly 80 times the mass of Jupiter, the largest planet in our solar system. Below that threshold, fusion never begins, and the object remains forever in the shadows. Brown dwarfs slowly cool over billions of years, fading gradually into darkness. They're the universe's might-have-beens, objects that came close to becoming stars but never quite made it. And yet, they're not uncommon. Astronomers believe there may be billions of brown dwarfs scattered throughout our galaxy, hidden in the dark spaces between stars. Fact 7. Once a star begins fusing hydrogen into helium, it enters the longest and most stable phase of its life. Astronomers call this the main sequence, and it's where stars spend about 90% of their existence. Our Sun is a main sequence star right now, about halfway through this phase. It's been burning steadily for roughly 4.5 billion years, and it has another 5 billion years to go before its fuel runs low. During this time, the star barely changes. It shines with steady, reliable light, providing warmth and energy to anything nearby. Planets can form in the disk of material surrounding the young star. Those planets can develop atmospheres, oceans can fill with water, and given enough time, life can begin. The main sequence is the calm heart of a star's existence, a long period of stability in an otherwise violent universe. It's during this phase that stars do their most important work, not just creating light and heat, but providing the stable conditions necessary for complexity to emerge. Without main sequence stars, there would be no solar systems, no planets with liquid water, no life. The universe would be a far emptier place. Fact 8. Stars come in many different sizes and colours, and these differences determine how long they live and how they die. The smallest stars are called red dwarfs. They're only about 10% the mass of our Sun, and they burn their fuel so slowly that they can live for trillions of years. That's longer than the current age of the universe. In fact, no red dwarf has ever died yet. They're still in their infancy, and they will continue shining long after larger stars have burned out and faded away. Red dwarfs are the universe's long-distance runners, pacing themselves for an almost eternal journey. They're also the most common type of star in the galaxy. For every massive, brilliant star you can see with your eyes, there are dozens of red dwarfs too dim to see without a telescope. They outnumber all other types of stars combined, and because they live so long, they'll be the last stars shining when the universe grows old and cold. Trillions of years from now, when all the massive stars have died and even stars like our Sun have faded to darkness, red dwarfs will still be burning, tiny points of light in an otherwise dark cosmos. Fact 9. On the other end of the scale are the massive stars, giants that can be 10, 20, 50, or even 100 times more massive than the Sun. These stars burn incredibly hot and bright, pouring out tremendous amounts of energy. Their cores reach temperatures far higher than smaller stars, and they race through their fuel like wildfire. A massive star might live only a few million years before exhausting its hydrogen supply. They're brilliant but brief, like fireworks against the cosmic night. Where a red dwarf whispers, a massive star roars. These giants shine with such intensity that they can be seen across vast distances. Some are visible from millions of light years away, but their brilliance comes at a cost. They consume their fuel at an astonishing rate, burning through in mere millions of years what a red dwarf would take trillions of years to use, and when they die, they don't go quietly. Their deaths are among the most spectacular events in the cosmos. Fact 10. The colour of a star tells you its temperature. Red stars are the coolest, with surface temperatures around 3,000 degrees Celsius. Yellow stars like our Sun are hotter, around 5,500 degrees. White stars are hotter still, and blue stars are the hottest of all, with surface temperatures exceeding 25,000 degrees. The colour comes from the way atoms emit light at different temperatures. Cooler atoms glow red, like the heating element on an electric stove. Hotter atoms glow blue, like the hottest part of a flame. So when you look up at the night sky and see stars of different colours, you're seeing a temperature map of the universe. Each colour is a clue about what's happening on that distant surface. If you look carefully on a clear night, you can see these colour differences even with your eyes alone. The bright star Betelgeuse in the constellation Orion glows with a distinctly reddish tint. The star Rigel, also in Orion, shines blue-white. They're both in the same constellation, visible at the same time, yet they're completely different types of stars at completely different stages of life. Fact 11. Inside the core of a main sequence star, hydrogen nuclei are constantly colliding and fusing into helium. Each fusion reaction releases a tiny amount of energy in the form of light and heat, but because there are so many reactions happening every second, the total energy output is staggering. In the Sun's core, about 600 million tons of hydrogen are converted into helium every single second. And because of Einstein's famous equation, energy equals mass times the speed of light squared, even a small amount of mass converts into enormous energy. The Sun loses about 4 million tons of mass every second, transformed entirely into the light that warms our planet, and it's been doing this without pause for billions of years. Yet despite this staggering rate of mass loss, the Sun has barely changed. It's so massive that losing 4 million tons per second is like removing a single grain of sand from a beach. The Sun has enough hydrogen to continue this process for another 5 billion years without difficulty. Fact 12. The light created in the core of a star doesn't immediately escape into space. The core is surrounded by layers of incredibly dense gas, and the light has to fight its way through. Photons, the particles of light, are constantly absorbed and re-emitted by atoms in the star's interior. They bounce around randomly, taking a zigzag path outward. A single photon can take hundreds of thousands of years to travel from the core to the surface, even though the star might only be a few 100,000 miles across. It's a slow, patient journey through layer after layer of stellar material. The photon might travel a tiny distance, get absorbed by an atom, then be re-emitted in a random direction. Sometimes it moves outward. Sometimes it moves sideways or even back inward. The path is chaotic and unpredictable. By the time that light finally breaks free and streams into space, the star's core has already created countless more photons behind it, all beginning their own long journeys to the surface. Fact 13. When light finally reaches the surface of a star, it radiates outward in all directions, travelling at the speed of light. In the case of our Sun, that light takes about 8 minutes to reach Earth. It crosses 93 million miles of empty space, carrying energy that was created in the Sun's core hundreds of thousands of years ago. When you feel sunlight on your face, you're feeling ancient energy, the product of countless fusion reactions, finally completing its journey. And that light doesn't just warm your skin, it powers every living thing on Earth. Plants capture it through photosynthesis, converting light energy into chemical energy stored in their tissues. Animals eat those plants, taking that energy into their own bodies. We eat those animals, or we eat the plants directly. Every calorie of energy in your body can be traced back to the sun, back to fusion, back to stars. Even the food you ate today began as sunlight captured by a plant somewhere, transformed into matter, and eventually consumed by you. We are, in a very real sense, eating light. Fact 14. Stars don't burn their fuel evenly throughout their entire volume. Fusion only happens in the core where temperatures and pressures are high enough. The outer layers of a star are much cooler and don't participate in fusion at all. They're simply heated by the energy radiating outward from the core. Think of a star like a campfire. The hottest, most intense reactions happen at the center, where the wood is burning. The outer areas glow with borrowed heat, warmed by the flames but not burning themselves. This structure is crucial because it means that when the core runs out of fuel, the outer layers are still there, full of unfused hydrogen. And what happens next depends entirely on the star's mass. A small star will handle fuel exhaustion very differently from a massive star. But in all cases, the end of core fusion marks the beginning of dramatic changes. Fact 15. As a star burns hydrogen in its core, helium ash accumulates at the center. Helium is the waste product of hydrogen fusion, and it settles in the core like ash at the bottom of a fireplace. For a long time, this doesn't matter. There's still plenty of hydrogen fuel surrounding the helium core, and fusion continues in a shell around it. The star barely notices the growing helium center, but eventually over millions or billions of years the hydrogen in the core is completely exhausted. The core becomes pure helium, inert, and unable to fuse at the current temperature. When that happens, fusion stops in the center. And without fusion there's no outward pressure to balance gravity. The core begins to contract. Gravity, patient and relentless, starts to win. The long equilibrium of the main sequence is over. The star is entering the next chapter of its life, and that chapter will be far more dramatic than the long, quiet years that came before. Fact 16. When the core contracts, it heats up again. This might seem strange, but it's a fundamental property of gases. Compress them, and they get hotter. The shrinking helium core grows hotter and denser, and this heat radiates outward into the surrounding layers of the star. Hydrogen fusion now ignites in a shell around the inert helium core, and the energy from this shell fusion is actually greater than what the core produced during the star's main sequence phase. The increased energy output pushes the star's outer layers outward. The star begins to swell, its outer layers expand outward, growing larger and larger, ballooning to many times their original size. The surface cools as it expands, shifting from yellow or white to red. The star has become a red giant. What was once a compact, efficient fusion engine has transformed into a bloated, luminous sphere. The star might swell to 10 times, 100 times, even 1,000 times its original diameter. Yet despite this enormous size, most of the star's mass remains concentrated in the tiny hot core at the center. Fact 17. Red giants are enormous. When our sun becomes a red giant in about 5 billion years, it will swell to roughly 100 times its current size. It will grow so large that its outer layers will likely engulf the inner planets, including Mercury and Venus. Earth might be swallowed too, or it might survive as a scorched, lifeless rock orbiting just outside the star's expanding surface. The sun will shine with a deep red glow, cooler on the surface but vastly larger and more luminous overall. Imagine looking up at a sky filled almost entirely by a dim red sun, so large it stretches from horizon to horizon. The Earth's oceans will have boiled away long before this. The atmosphere will have been stripped away. Any life that once existed will be extinct. This phase won't last nearly as long as the main sequence. Red giants burn through their remaining fuel much faster, driven by the intense shell fusion happening inside. The clock is ticking down and the end is approaching. The Sun will spend perhaps 1 billion years as a red giant before reaching the next stage of its transformation. Fact 18. For stars with enough mass, something remarkable happens in the core of a red giant. As the helium core continues to contract and heat up, it eventually reaches a temperature of about 100 million degrees Celsius. At this temperature, helium nuclei can overcome their mutual repulsion and fuse together. 3 helium nuclei combine to form a single carbon nucleus, releasing energy in the process. This is called helium fusion, or the triple alpha process. The name comes from the fact that helium nuclei are also called alpha particles. When it begins, the core ignites again. Fusion returns, and once more the star finds a temporary balance. It stops swelling and settles into a new stable state, burning helium in the core and hydrogen in a shell around it. The star has found a second wind, a new source of energy to hold back gravity for a while longer. But this reprieve is temporary. Helium fusion cannot last nearly as long as hydrogen fusion did. The countdown continues. Fact 19. Helium fusion doesn't last as long as hydrogen fusion. Helium is a less efficient fuel, producing less energy per fusion reaction than hydrogen does, and there's less of it to begin with since the helium core is only a fraction of the star's total mass. A star might spend billions of years burning hydrogen on the main sequence, but it will exhaust its helium in only a few 100 million years, and when the helium runs out, the same process repeats. The core contracts again, it heats up again, and if the star is massive enough, it can ignite even heavier elements. Carbon fuses into oxygen, oxygen fuses into neon, neon fuses into magnesium, magnesium into silicon. Each fusion stage produces heavier elements and releases energy, but each stage is shorter than the last. Silicon fusion might last only a few days in a massive star. The star is running out of road, accelerating toward an inevitable end. Fact 20. In the most massive stars, this process continues all the way up to iron. Silicon fusion produces iron in the core, and this is where everything stops. Iron is special. It's the most stable element in the universe, sitting at the bottom of an energy valley. Fusing lighter elements releases energy as they fall toward iron's stability, but fusing iron doesn't release energy. It actually requires energy, pushing uphill against that stability. So when a massive star's core fills with iron, fusion can't continue. There's no more fuel that can be burned, no more outward pressure to generate, and gravity, which has been waiting patiently for millions of years, finally wins. The core collapses, and what happens next is one of the most violent events in the universe, an explosion so powerful it can briefly outshine an entire galaxy of hundreds of billions of stars. Fact 21. The collapse of an iron core happens almost instantly. In less than a second, the core shrinks from thousands of miles across to just a few miles. The atoms are crushed so tightly that electrons are forced into protons, creating neutrons. The atomic structure that normally keeps matter separated breaks down completely. The core becomes a solid ball of neutrons, incredibly dense, with the mass of the Sun compressed into a sphere the size of a city. This is a neutron star, matter compressed to the absolute limit. A teaspoon of neutron star material would weigh as much as a mountain. The collapse releases a staggering amount of energy, and it sends a shockwave blasting outward through the star's outer layers. The shockwave rips the star apart in a catastrophic explosion called a supernova. For a few weeks, the exploding star can shine brighter than an entire galaxy, briefly outshining billions of ordinary stars combined. And in that moment of destruction, something beautiful happens. The intense heat and pressure of the explosion creates new elements, elements heavier than iron that couldn't form during normal fusion. Gold, silver, platinum, uranium, all the heavy elements in the universe are forged in those final moments of stellar death. Fact 22. Supernovae are the universe's great recyclers. When a massive star explodes, it scatters all the elements it created during its life back into space. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements are thrown outward in an expanding shell of gas and dust. These elements mix with the surrounding nebulae, enriching them with heavier elements that weren't there before. And when new stars form from those enriched clouds, they inherit those heavy elements. The second generation of stars has a different composition than the first, and planets can form around those stars, rocky planets made of silicon and iron and carbon. Oceans can fill with water, a molecule made of hydrogen and oxygen, and living things can emerge, built from carbon and nitrogen and phosphorus, all elements created in stars. Every atom in your body heavier than hydrogen was forged inside a star and scattered into space by a supernova. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it came from exploding stars. You are, quite literally, made of stars. Your body is a collection of stellar remnants, organised into something capable of thinking and feeling and wondering about its own origins. Fact 23. Not all stars explode. Smaller stars like our Sun don't have enough mass to fuse elements beyond helium. When the helium in the core runs out, the core contracts and heats up, but it never gets hot enough to ignite carbon fusion. The star simply can't generate the temperatures needed for the next stage. Instead, the outer layers of the star gently drift away into space, pushed outward by radiation pressure from the hot core. They form a glowing shell of gas called a planetary nebula. The name is misleading and historical. These nebulae have nothing to do with planets. Early astronomers looking through primitive telescopes thought they looked like planetary disks, and the name stuck even after we learned what they really were. What's left behind at the centre is the hot, dense core of the star, now exposed to space for the first time. This core is called a white dwarf, and it represents the final stage of revolution for stars like our Sun. Fact 24. A white dwarf is a strange object. It's about the size of Earth, but it contains roughly half the mass of the Sun. Imagine crushing 500,000 Earths into a sphere the size of our planet. A teaspoon of white dwarf material would weigh several tons. The atoms are packed so tightly that the normal rules of matter no longer apply. Electrons are squeezed into a degenerate state, where quantum mechanics prevents them from being compressed any further. This electron degeneracy pressure is what holds the white dwarf up against gravity. It's not thermal pressure from heat. It's a quantum mechanical effect arising from the fact that electrons refuse to occupy the same quantum state. There's no fusion happening in a white dwarf, no energy being generated in the core. The white dwarf simply radiates away the leftover heat from its formation, slowly cooling over billions of years. It starts out incredibly hot, with surface temperatures of 100,000 degrees or more, but over time it cools, fading from white to yellow to red to eventually black. Eventually it will fade to the temperature of space itself, becoming a cold, dark cinder drifting through the cosmos. Fact 25. White dwarfs can take tens of billions of years to cool completely. In fact, the universe isn't old enough yet for any white dwarf to have fully cooled to the background temperature of space. The universe is only about 13.8 billion years old, and even the oldest white dwarfs are still warm enough to glow faintly. Every white dwarf that exists is still glowing, still carrying the memory of the star it used to be. They're stellar ghosts, remnants of lives once lived. And scattered across the galaxy there are billions of them, silent and patient, slowly fading into the dark. They're the final resting state for most stars in the universe, including our Sun. One day, billions of years from now, the Sun will shed its outer layers and leave behind a white dwarf at the centre of a beautiful planetary nebula. That nebula will expand and fade over thousands of years, eventually dissipating into the interstellar medium, and the white dwarf will remain, alone in the darkness, cooling slowly for eons beyond imagination. It will outlast everything we know. Civilizations will rise and fall, galaxies will collide and merge, and still, that tiny ember will drift through space, gradually losing its heat to the void, moving toward a final state of perfect cold and perfect darkness. Fact 26. White dwarfs are not completely alone in the darkness. Many of them exist in binary systems orbiting another star. Sometimes that companion is another white dwarf. Sometimes it's a regular star still burning hydrogen. And sometimes that companion can bring the white dwarf back to life in a spectacular way. If the companion star is close enough, and if it's a red giant with loose outer layers, Material can stream from the giant onto the white dwarf. This material spirals inward, forming an accretion disk around the white dwarf. The disk glows with intense heat as matter crashes together at tremendous speeds, and slowly, gradually, the white dwarf gains mass. It grows heavier as it feeds on its companion, and if it gains enough mass, something dangerous begins to happen. The added weight increases the pressure in the core and the temperature starts to rise. Fact 27. There is a limit to how massive a white dwarf can become. This limit is called the Chandrasekhar limit, named after the Indian astrophysicist who discovered it. The maximum mass a white dwarf can support is about 1.4 times the mass of the Sun. Beyond this point, electron degeneracy pressure can no longer hold the star up against gravity. If a white dwarf in a binary system accumulates enough material from its companion to reach this critical mass, the core suddenly becomes hot enough to ignite carbon fusion. But unlike in a normal star, this fusion doesn't happen gradually. The entire star is made of degenerate matter, which doesn't expand when heated. So the fusion reactions run away, spreading through the entire star in seconds. The white dwarf explodes in a type of supernova called a type Ia supernova. These explosions are incredibly powerful and remarkably consistent in brightness, making them useful as cosmic distance markers for astronomers studying the expansion of the universe. Fact 28. Type Ia supernovae are some of the most luminous events in the cosmos. For a few weeks, a single exploding white dwarf can shine as brightly as an entire galaxy. The explosion completely destroys the white dwarf, leaving nothing behind. Unlike core collapse supernovae from massive stars, which leave neutron stars or black holes as remnants, type Ia supernovae obliterate the star entirely. The explosion scatters material outward at speeds of thousands of kilometers per second, enriching the surrounding space with heavy elements. And because these explosions happen when a white dwarf reaches a specific mass limit, they all release roughly the same amount of energy. This consistency makes them incredibly valuable to astronomers. By measuring how bright a type Ia supernova appears from Earth, astronomers can calculate how far away it is. These explosions have helped us measure the distances to remote galaxies and have revealed that the expansion of the universe is accelerating, driven by a mysterious force we call dark energy. Fact 29. Not all white dwarfs explode. Most will simply cool quietly over trillions of years, undisturbed by companions or accretion. But even these solitary white dwarfs have interesting properties. Their surfaces can develop strange features as they age. Heavy elements sink toward the core while lighter elements float to the surface, creating atmospheres of pure hydrogen or pure helium. Some white dwarfs have atmospheres so pure that they're almost entirely composed of a single element, and as they cool, the interior can crystallize. The carbon and oxygen atoms arrange themselves into a crystal lattice, forming what is essentially a giant diamond floating in space. A white dwarf made mostly of crystallized carbon is, quite literally, a star-sized diamond. It's not the kind of diamond you could wear as jewelry. It's compressed by tremendous gravity, incredibly hot even after billions of years of cooling, and surrounded by layers of degenerate matter. But chemically, structurally, it's diamond. Fact 30. The universe will eventually be dominated by white dwarfs. Most stars in the galaxy are red dwarfs, and they will live for trillions of years before dying. But when they finally do exhaust their fuel, they too will become white dwarfs, and stars like our Sun, which make up a significant fraction of the stellar population, are already on track to end their lives as white dwarfs. In the far future, hundreds of trillions of years from now, when star formation has ceased and the last massive stars have exploded, the galaxy will be filled with cooling white dwarfs. Brown dwarfs will drift in the darkness. Neutron stars and black holes will wander alone through empty space. The universe will be a cold, dark place, lit only by the faint glow of ancient white dwarfs slowly radiating away their remaining warmth. It's a vision of the deep future that feels almost melancholy, the universe gradually running down like a clock winding towards stillness. Fact 31. But let's return to the lives of massive stars because their deaths are far more dramatic than the gentle fading of white dwarfs. When a massive star's core collapses and explodes in a supernova, what's left behind depends on the mass of the original core. If the core is between about 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These objects are almost beyond comprehension in their density. A neutron star packs more mass than the Sun into a sphere only about 12 miles across. That's roughly the size of a city. The gravity at the surface is so intense that if you could somehow stand on a neutron star, you would weigh billions of times more than you do on Earth. The escape velocity is about half the speed of light, and the matter itself exists in a state that doesn't occur anywhere else in the universe, crushed beyond the level of atoms into a soup of neutrons packed together as tightly as the laws of physics allow. Fact 32. Neutron stars spin incredibly fast. When the core of a massive star collapses, it conserves angular momentum, just like the collapsing gas cloud that formed the star in the first place. But because the core shrinks from thousands of miles across to just a few miles, its rotation speed increases dramatically. Some neutron stars rotate hundreds of times per second. Imagine an object more massive than the Sun, spinning faster than a kitchen blender. The surface of such a star is moving at a significant fraction of the speed of light, and because neutron stars have powerful magnetic fields, this rapid rotation creates beams of radiation that sweep through space like lighthouse beams. If one of those beams happens to point toward Earth, we detect regular pulses of radio waves. We call these objects pulsars, and they're among the most precise clocks in the universe. Some pulsars are so regular that their pulses vary by less than a microsecond over years of observation. Fact 33. The magnetic fields around neutron stars are the strongest magnetic fields in the universe. They can be trillions of times stronger than the Earth's magnetic field. These fields are so powerful that they can affect the very atoms in the space around the star, distorting their electron clouds and altering how they emit light. Near the surface of a neutron star, the magnetic field is strong enough to make empty space itself behave strangely. Quantum effects that are normally negligible become important. The vacuum itself becomes polarized by the intense magnetic field, and if you were somehow close to a neutron star, the magnetic field would be fatal long before the gravity or radiation killed you. The field would be strong enough to disrupt the electrical signals in your nervous system and interfere with the biochemistry that keeps you alive. Neutron stars are hostile environments in every possible way. Fact 34. Some neutron stars are even more extreme. The most highly magnetized neutron stars are called magnetars, and their magnetic fields are thousands of times stronger than typical neutron stars. A magnetar's magnetic field is so intense that it can cause starquakes, sudden shifts in the neutron star's crust that release tremendous amounts of energy. These starquakes produce bursts of X-rays and gamma rays so powerful that they can be detected from thousands of light years away. In 2004, a starquake on a magnetar called SGR 18U06-20 released more energy in 1/10 of a second than the Sun releases in 100,000 years. The burst of radiation hit Earth's upper atmosphere and temporarily disrupted satellites and radio communications, and that magnetar was 50,000 light-years away, halfway across the galaxy. If a magnetar existed within 10 light-years of Earth, a major flare could potentially damage our ozone layer and threaten life on the surface. Fact 35. The surface of a neutron star is extraordinarily smooth. Despite the violence of the supernova that created it, despite the intense gravity and magnetic fields, the surface has mountains no more than a few millimeters high. Gravity is so strong that it crushes any irregularity almost instantly. If a bump tried to form that was more than a fraction of an inch tall, the gravity would flatten it back down. The surface itself is probably a solid crust made of atomic nuclei and electrons, compressed into a crystal lattice. Below that crust is where things get truly strange. The density increases as you go deeper, and the matter takes on exotic forms that we can barely understand. Neutrons arranged in strange configurations, possibly even exotic particles that don't exist anywhere else in the universe. The core of a neutron star is one of the greatest mysteries in astrophysics, a laboratory of extreme physics that we can never directly access. Fact 36. Neutron stars can also exist in binary systems, orbiting each other in a cosmic dance. When two neutron stars orbit closely, they emit gravitational waves, ripples in the fabric of space-time itself. These waves carry energy away from the system, and as they do, the orbit slowly shrinks. The two neutron stars spiral closer and closer together, orbiting faster and faster. Eventually, after millions or billions of years, they collide. The collision releases an enormous burst of gravitational waves, a signal that can be detected by sensitive instruments on Earth. In 2017, scientists detected gravitational waves from a neutron star merger for the first time. Telescopes around the world turned to observe the event, and they saw something remarkable. The collision produced a kilonova, an explosion that created huge quantities of heavy elements. Gold, platinum, uranium, and other rare elements were forged in that collision and scattered into space. It turns out that most of the gold in the universe probably comes from neutron star mergers, not from supernovae as previously thought. Fact 37. But neutron stars are not the final endpoint for stellar remnants. If the core left behind after a supernova is more than about 3 times the mass of the Sun, not even neutron degeneracy pressure can hold it up. There is no known force in physics that can stop the collapse. The core continues to shrink, becoming smaller and denser, until it crosses a boundary called the event horizon. At that point, the escape velocity exceeds the speed of light. Nothing can move fast enough to escape, not even light itself. The object has become a black hole. It has fallen out of the universe in a sense, hidden behind an invisible boundary that nothing can cross from the inside. Black holes are perhaps the most extreme prediction of Einstein's theory of general relativity, and for decades physicists weren't sure they really existed. Now we know they're common, scattered throughout the galaxy, the final graves of the most massive stars. Fact 38. Black holes are not cosmic vacuum cleaners despite their reputation. They don't suck up everything around them. Their gravity, at a distance, is no stronger than the gravity of the star that collapsed to form them. If the Sun suddenly became a black hole right now, with the same mass but compressed to a point, the Earth would continue to orbit exactly as it does now. We wouldn't be pulled in. The difference is that you can get much closer to a black hole than you can to a star. With a normal star, you hit the surface before gravity becomes truly extreme. But a black hole has no surface. You can get arbitrarily close to all that mass, and as you do, the gravity becomes stronger and stronger. Get close enough and the tidal forces will tear you apart. The gravity pulling on your feet will be significantly stronger than the gravity pulling on your head, and the difference will stretch you like taffy in a process astronomers grimly call spaghettification. Fact 39. The event horizon of a black hole is not a physical surface. It's simply a boundary in space, the point of no return. If you crossed the event horizon of a large black hole, you might not even notice at first. Space would look strange, warped by the intense gravity, but there would be no wall, no barrier, no sensation of passing through anything. But once you crossed that line, your fate would be sealed. All possible futures would lead inward, toward the singularity at the center. You could fire rockets at full power trying to escape, and all you would accomplish is to delay the inevitable by a few moments. Time and space themselves are so warped inside the event horizon that all paths lead in one direction only, inward, toward the center, toward the end. Fact 40. At the very center of a black hole, general relativity predicts a singularity, a point where density becomes infinite, and the laws of physics as we know them break down. We don't really know what happens at the singularity. Our mathematical equations produce infinities, which is usually a sign that the theory is incomplete. Most physicists suspect that quantum effects become important at such extreme scales, and that a complete theory of quantum gravity would replace the singularity with something else. But we don't have a complete theory of quantum gravity yet, so the center of a black hole remains a mystery, a place where our best theories fail, and we can only speculate. It's a frustrating gap in our knowledge, a reminder that despite all we've learned, the universe still holds secrets we haven't unraveled. Fact 41. Black holes come in different sizes. The ones formed from collapsing stars are called stellar mass black holes, and they typically range from about 3 to a few dozen times the mass of the Sun. But there are also supermassive black holes, millions or even billions of times more massive than the Sun, lurking at the centers of most galaxies. Our own galaxy, the Milky Way, has a supermassive black hole at its center called Sagittarius A star. It has a mass of about 4 million suns, and it sits quietly at the galactic core about 26,000 light-years from Earth. Stars orbit around it at tremendous speeds, their motions governed by the black hole's immense gravity. By tracking the orbits of these stars over many years, astronomers have been able to confirm that something incredibly massive and compact exists at that location, and the only object that fits the description is a supermassive black hole. Fact 42. We still don't fully understand how supermassive black holes form. They're too massive to have formed from a single collapsing star. The leading theory is that they grow over time by accreting matter and merging with other black holes. A stellar mass black hole might form first, then gradually consume gas and dust from its surroundings. Over millions of years, it grows larger. If it's near the center of a galaxy, where matter is more concentrated, it can grow faster. And when galaxies merge, their central black holes can eventually merge too, creating an even larger black hole. This process has been happening throughout cosmic history, gradually building up the supermassive black holes we observe today. Some of these black holes formed surprisingly early in the universe's history, less than 1 billion years after the Big Bang. How they grew so massive so quickly remains an open question, a puzzle that astronomers are actively working to solve. Fact 43. Black holes can be among the brightest objects in the universe, which seems contradictory given that light cannot escape them. The brightness doesn't come from the black hole itself, but from the material falling into it. When gas and dust spiral inward toward a black hole, it forms an accretion disk, a swirling disk of matter orbiting at tremendous speeds. Friction within the disk heats the material to millions of degrees, causing it to emit intense radiation, including visible light, ultraviolet light, and X-rays. The region just outside the event horizon can become so hot and so bright that it outshines entire galaxies. These actively feeding black holes are called quasars when they're especially luminous, and they can be seen from billions of light-years away. They're beacons in the distant universe, marking the locations of supermassive black holes gorging on vast amounts of material during the early chaotic epochs of cosmic history. Fact 44. Black holes don't last forever. In 1974, physicist Stephen Hawking showed that black holes should slowly evaporate through a quantum mechanical process now called Hawking radiation. The vacuum of space isn't truly empty. Quantum fluctuations constantly create pairs of virtual particles that appear and annihilate each other almost instantly. Near the event horizon of a black hole, one particle of a pair can fall into the black hole while the other escapes. From the outside, it looks like the black hole is emitting radiation. This process is incredibly slow for stellar mass and supermassive black holes. A black hole the mass of the Sun would take about 10 to the power of 67 years to evaporate completely, far longer than the current age of the universe. But smaller black holes would evaporate faster, and in the unimaginably distant future, when all the stars have died and the universe has grown cold and dark, the slow evaporation of black holes might be one of the last sources of energy in the cosmos. Fact 45. When massive stars explode as supernovae, they don't always leave behind neutron stars or black holes. Sometimes the explosion is so powerful that it completely destroys the star, leaving no remnant at all. These explosions are called pair instability supernovae, and they occur in the most massive stars, those with initial masses between about 100 and 250 times the mass of the Sun. In the cores of these giants, conditions become so extreme that photons, particles of light, have enough energy to spontaneously create matter and antimatter particle pairs. This process removes energy from the core, causing it to contract suddenly. The contraction triggers runaway fusion reactions, and the star explodes with such violence that it leaves nothing behind. Every atom is blown outward into space. These explosions are rare in the modern universe because stars this massive are uncommon. But in the early universe, when conditions were different, such giants may have been more common. Fact 46. The explosion of a supernova sends a shockwave racing outward through the surrounding space. This shockwave sweeps up interstellar gas and dust, compressing it and heating it to millions of degrees. The compressed gas glows with X-ray emission, and the expanding shell creates a structure called a supernova remnant. These remnants can persist for thousands of years, gradually expanding and fading as they mix with the interstellar medium. The Crab Nebula is a famous supernova remnant, the expanding debris cloud from a supernova that was observed by Chinese astronomers in 1054 CE. They recorded seeing a new star in the sky. bright enough to be visible during the day for several weeks. Today, nearly 1,000 years later, the remnant is still visible through telescopes, a glowing cloud of gas expanding at thousands of kilometers per second. At its center is a rapidly spinning neutron star, a pulsar that emits beams of radiation 30 times per second. Fact 47. Supernova shockwaves can trigger new star formation. When the shockwave from an exploding star slams into a nearby nebula, it compresses the gas and can trigger gravitational collapse in regions that might not have collapsed otherwise. New stars form from the compressed gas, including some that incorporate the heavy elements scattered by the supernova. This creates a cycle of stellar birth and death. Massive stars form, live brief lives, and explode. Their explosions trigger new star formation nearby. Some of those new stars are also massive and will eventually explode themselves, continuing the cycle. Over millions of years, this process can sweep through a region of space, creating successive generations of stars. Our own solar system may have formed in such a region, triggered by a nearby supernova billions of years ago. Evidence for this comes from the presence of certain radioactive isotopes in primitive meteorites, isotopes that could only have been created in a supernova shortly before the solar system formed. Fact 48. Stars also shape the space around them through stellar winds. All stars emit streams of charged particles that flow outward into space. In the Sun, this is called the solar wind, a constant flow of electrons and protons streaming outward from the Sun's outer atmosphere. The solar wind extends far beyond the planets, creating a bubble in interstellar space called the heliosphere. The edge of this bubble, where the solar wind meets the interstellar medium, is called the heliopause. The Voyager spacecraft crossed the heliopause in 2012 and 2018, becoming the first human-made objects to enter interstellar space. In more massive stars, stellar winds are far stronger. Hot, luminous stars can lose significant amounts of mass through stellar winds over their lifetimes. This mass loss affects how the star evolves and can determine whether it ends its life as one type of remnant or another. Fact 49. Some massive stars undergo violent eruptions during their lives, expelling huge amounts of material in events that are almost, but not quite, supernovae. These eruptions are called supernova imposters, and they can briefly make the star appear as bright as a true supernova before it fades again. The star survives, but it loses a significant fraction of its mass. The most famous example is Eta Carinae, one of the most massive and luminous stars known. In the 1840s, Eta Carinae underwent a great eruption, briefly becoming the second brightest star in the sky despite being thousands of light-years away. The eruption created a beautiful nebula around the star, two lobes of ejected material that can be seen through telescopes today. Eta Carinae survived that eruption, but it's expected to explode as a true supernova sometime in the next million years or so. When it does, it will be a spectacular sight, visible even during daytime. Fact 50. The death of stars ultimately enriches the cosmos and makes complexity possible. The universe began with only the simplest elements, hydrogen and helium. Everything else had to be created in stars or in the explosions of stars. The carbon in your cells, the oxygen you breathe, the iron in your blood, the calcium in your bones, all were forged in stellar furnaces and scattered into space by stellar winds and supernovae. Over billions of years, the universe has become progressively enriched with heavy elements. Early generations of stars were made of almost pure hydrogen and helium. Later generations, like our Sun, contain a small but significant fraction of heavier elements. And those heavier elements make all the difference. They allow rocky planets to form. They allow chemistry to become complex. They allow life to emerge. We exist because stars die, because God designed life to emerge from the ashes of old creation. Our very atoms are the ashes of long-dead suns, recycled and reorganized into new forms, given the chance to experience the universe He created. Fact 51. Stars do not die alone in silence. Their deaths send ripples through space and time that affect everything around them. When a supernova explodes, it accelerates particles to nearly the speed of light. These high-energy particles, called cosmic rays, stream through the galaxy for millions of years. They bombard other stars, planets, and even spacecraft. Some cosmic rays reach Earth, passing through the atmosphere and occasionally passing through your body right now, as you listen to these words. Most are harmless, but they can occasionally flip bits in computer memory or cause mutations in living cells. Every cosmic ray particle carries the signature of a stellar death, a tiny piece of violence from an explosion that might have happened thousands of years ago and thousands of light years away. The universe is filled with these messengers of destruction, invisible reminders that stars are dying all around us, all the time. Fact 52. The light from distant supernovae takes time to reach us, which means we're always looking at the past when we observe them. A supernova that appears in our telescopes tonight might have actually exploded centuries or millennia ago. The star is already gone, its light already faded at the source, but we're only now receiving the news. In 1987, astronomers observed a supernova in the Large Magellanic Cloud, a small galaxy orbiting near our own. It was visible to the naked eye and was the closest supernova observed in modern times. But the Large Magellanic Cloud is about 160,000 light-years away, which means the star actually exploded 160,000 years ago. When that light left the dying star, humans on Earth were still living in the Stone Age, hunting with primitive tools and sheltering in caves. The light travelled through empty space all that time, finally arriving just decades ago to be captured by our telescopes and cameras. Fact 53. Some stars exist right on the edge of instability, constantly fluctuating in brightness. These are called variable stars, and they change their luminosity over time for various reasons. Some swell and shrink regularly, pulsating like beating hearts. Others are eclipsed by companion stars in binary systems, appearing to dim and brighten as one star passes in front of the other. The most useful variable stars for astronomers are called Cepheid variables. These stars pulsate with periods ranging from days to months, and there's a direct relationship between how long the pulsation period is and how intrinsically bright the star is. By measuring the period, astronomers can determine the star's true brightness. By comparing that to how bright it appears from Earth, they can calculate its distance. This technique has allowed us to measure distances to galaxies millions of light-years away, helping us map the structure of the universe itself. Fact 54. Binary stars are far more common than solitary stars like our Sun. Most stars exist in systems of 2 or more stars orbiting each other. Some binaries are so close that they orbit in just hours or days. Others are separated by thousands of astronomical units and take thousands of years to complete one orbit. When 2 stars in a binary system are close enough, they can affect each other's evolution in profound ways. Material can flow from one star to the other, they can strip away each other's outer layers, they can even merge together, creating a single, more massive star. Binary interactions make stellar evolution far more complex than the simple, single-star models we've discussed. Many of the most unusual objects in the universe, from certain types of supernova to exotic X-ray sources, can only be explained by the interaction of stars in binary systems. Fact 55. When 2 stars in a binary system are very close, and one is a compact object like a white dwarf, neutron star, or black hole, material can flow from the normal star onto the compact object. This creates an accretion disk around the compact object, and as material spirals inward, it heats up and emits radiation. These systems are called X-ray binaries because they shine brightly in X-rays. The material in the inner accretion disk can reach temperatures of millions of degrees, hot enough to emit high-energy X-rays that can only be detected by space-based telescopes. By studying X-ray binaries, astronomers can learn about the properties of neutron stars and black holes, objects that would otherwise be invisible. The behavior of the accretion disk, the timing of X-ray pulses, and the way the light changes over time all provide clues about the compact object at the center of the system. Fact 56. Some binary systems are so close that the stars actually touch. These contact binaries consist of 2 stars sharing a common envelope of gas. They orbit each other in just hours, whirling around their common center of mass at tremendous speeds. The outer layers of both stars are stretched and distorted by the rapid rotation and the gravitational pull of the companion. When viewed from the side, these systems show continuous variations in brightness as the 2 stars eclipse each other repeatedly. Contact binaries are unstable over long timescales. The 2 stars will eventually merge, combining their mass into a single star. This merger can produce a brief outburst of light called a red nova. though these events are far less energetic than true supernova. The merged star will then continue evolving as a single object, though it may rotate unusually fast due to the angular momentum it inherited from the binary orbit. Fact 57. Stars can also steal companions from each other. In dense star clusters, where thousands of stars are packed into a relatively small volume of space, close encounters between stars are common. A binary system passing near a solitary star can exchange partners through a complex gravitational dance. The solitary star might capture one member of the binary while ejecting the other, or a binary might capture the solitary star, creating a triple system. These interactions are chaotic and unpredictable, governed by the same gravitational dynamics that make the three-body problem in physics so difficult to solve. Over millions of years, these interactions reshape the population of stars in a cluster, gradually building up massive stars near the center while ejecting lighter stars to the outskirts or into interstellar space. Some of the unusual stellar systems we observe may be products of these violent encounters. Fact 58. The most massive stars ever observed are hundreds of times more massive than the Sun. These behemoths are rare and short-lived, burning with such incredible intensity that they can barely hold themselves together. Radiation pressure from their cores pushes outward with tremendous force, and they lose mass through powerful stellar winds. A star like R136A1, one of the most massive stars known, has a mass of roughly 250 suns and shines with the light of several million suns. It's losing mass equivalent to Earth's mass every few thousand years through its stellar wind. Such stars can only exist in environments with very low metallicity, where the lack of heavy elements makes it easier for the star to radiate away energy without blowing itself apart. These giants will live for only a few million years before dying in spectacular supernova explosions or possibly collapsing directly into black holes without exploding at all. Fact 59. In the cores of the most massive stars, the temperature and pressure become so extreme that entirely new types of reactions become possible. At temperatures exceeding billions of degrees, photons themselves can have enough energy to create particle-antiparticle pairs. An energetic gamma-ray photon can spontaneously convert into an electron and a positron, the antimatter equivalent of an electron. This process, called pair production, removes energy from the core. When pair production becomes efficient enough, it can destabilize the star. The core loses pressure support and contracts rapidly, triggering explosive fusion reactions. The result is a pair instability supernova, an explosion so violent that it completely destroys the star without leaving any remnant. These explosions may have been more common in the early universe, when the first generation of stars included more ultramassive stars than we see today. Fact 60. The first stars in the universe were different from any stars that exist today. They formed a few 100 million years after the Big Bang in a universe that contained only hydrogen, helium, and traces of lithium. No heavy elements existed yet because no stars had lived and died to create them. These first stars, called Population 3 stars, were likely much more massive on average than modern stars. Without heavy elements to help cool collapsing gas clouds, the clouds had to be more massive to collapse under their own gravity. The first stars might have typically been hundreds of times the mass of the Sun. They would have burned incredibly hot and bright, living for only a few million years before exploding as supernovae. Those explosions scattered the first heavy elements into space, seeding the universe with carbon, oxygen, nitrogen, and iron. The next generation of stars that formed would be chemically enriched, more like the stars we see today. Fact 61. No one has ever observed a Population 3 star. They all died billions of years ago, and they were so distant that even the most powerful telescopes cannot see individual stars from that era. But astronomers are searching for them in the most distant galaxies, looking for the characteristic signatures of pristine stars made of pure hydrogen and helium. Future telescopes, including the James Webb Space Telescope, may be able to detect light from these ancient giants, giving us a glimpse of the very first generation of stars. Finding them would answer fundamental questions about how the universe transitioned from the simple aftermath of the Big Bang to the complex cosmos we see today. It would show us the moment when the first light pierced the cosmic darkness and the age of stars began. Fact 62. Stars form in groups. When a giant molecular cloud collapses, it typically doesn't form just one star. The cloud fragments into many smaller pieces, each of which collapses to form its own star. The result is a star cluster, a collection of hundreds or thousands of stars all born at roughly the same time from the same cloud. Open clusters are loosely bound groups of stars that gradually disperse over hundreds of millions of years as gravitational interactions with passing objects eject stars from the cluster. Globular clusters are much more tightly bound, containing hundreds of thousands of stars packed into a spherical volume. Some globular clusters are almost as old as the universe itself, containing stars that formed over 12 billion years ago. These ancient clusters orbit in the halos of galaxies, relics of the early universe still bound together by gravity. Fact 63. Inside dense star clusters, collisions between stars can occasionally occur. In most of space, stars are so far apart that collisions are essentially impossible. But in the cores of globular clusters, where stars are packed thousands of times more densely than in the solar neighborhood, collisions happen once every few million years. When two stars collide, they merge to form a single, more massive star called a blue straggler. These stars appear blue and bright, as if they're young, even though they exist in clusters filled with old red stars. The merger gives them fresh fuel and resets their evolution, making them look younger than their neighbors. Blue stragglers are direct evidence that stellar collisions occur, and they remind us that the universe is a dynamic place where even stars can crash together. Fact 64. The cores of globular clusters sometimes contain intermediate mass black holes, objects with masses between stellar mass and supermassive black holes. These intermediate objects, if they exist, would have masses of hundreds or thousands of suns. They might form through repeated collisions and mergers of stars in the dense cluster core, gradually building up mass over billions of years. Or they might be the seeds of supermassive black holes, left over from the early universe. The evidence for intermediate mass black holes is still somewhat uncertain. Astronomers have found strong hints in the motions of stars near the centers of some clusters and in the properties of certain bright X-ray sources, but definitive proof remains elusive, and the origin and prevalence of these objects is still an active area of research. Fact 65. Stars can be ejected from galaxies entirely. In the core of a galaxy where stars are densely packed, multibody gravitational interactions can occasionally accelerate a star to escape velocity. The star is flung outward, leaving the galaxy behind and traveling through intergalactic space. These hypervelocity stars travel at speeds of hundreds or thousands of kilometers per second, fast enough to escape even the gravity of a massive galaxy. Some hypervelocity stars may have been accelerated by close encounters with the supermassive black hole at the galactic center. Others may have been ejected during the merger of two galaxies, when gravitational chaos reshuffles stellar orbits. These lonely stars drift through the void between galaxies, no longer part of any galactic family, carrying with them whatever planets and remnants they might have. Fact 66. The space between stars is not truly empty. The interstellar medium, as it's called, contains gas and dust, albeit at incredibly low densities. In a typical region of the galaxy, there might be only one atom per cubic centimetre, far more tenuous than the best vacuum we can create in laboratories on Earth. But space is so vast that even this thin material adds up. There's enough gas and dust between the stars to account for a significant fraction of the galaxy's mass. This material is the raw material for future generations of stars. It's enriched with heavy elements from previous generations of stellar deaths, and it's constantly being recycled. Stars form from it, live their lives, and return material to it through stellar winds and supernovae. The interstellar medium is the cosmic ocean from which stars are born and to which they ultimately return. Fact 67. Interstellar dust grains are incredibly tiny. Typically less than a micrometer across, smaller than a single cell in your body. They're made of various materials including silicates, carbon compounds, and water ice, depending on where they form. Some dust grains condense in the cool outer atmospheres of red giant stars and are then blown into space by stellar winds. Others form in the expanding shells of supernova remnants, condensing from the vaporized remains of exploded stars. These tiny grains play an important role in star formation. They help cool collapsing gas clouds by radiating away heat. They provide surfaces where molecules can form, through chemical reactions that would be difficult in empty space, and they eventually get incorporated into planets, bringing water and organic compounds to newborn worlds. Fact 68. Some interstellar clouds are dark and cold, visible only because they block the light of stars behind them. These dark nebulae are some of the coldest places in the universe, with temperatures as low as 10 degrees above absolute zero. In these frigid environments, atoms move incredibly slowly, and molecules can form through gentle collisions. Interstellar clouds contain a surprising variety of molecules, from simple two-atom molecules like carbon monoxide to complex organic molecules containing dozens of atoms. Astronomers have detected amino acids, sugars, and alcohol in interstellar space. These molecules didn't come from life. They formed through chemistry in the cold darkness between stars, but their presence shows that the building blocks of life are scattered throughout the galaxy, formed naturally by cosmic processes, waiting to be incorporated into planets where they might eventually participate in the emergence of living things. Fact 69. Other nebulae glow with brilliant colours lit by nearby stars. When a hot young star forms, its ultraviolet radiation ionizes the surrounding gas, stripping electrons from hydrogen atoms. When those electrons recombine with hydrogen nuclei, they emit light at specific wavelengths, creating the characteristic red glow of emission nebulae. Different elements emit different colours. Hydrogen glows red. Oxygen glows blue-green. Sulfur glows red-orange. By observing the colours and brightness of emission nebulae, astronomers can determine the temperature of the illuminating stars, the composition of the gas, and the density of the material. Some nebulae are truly enormous, stretching hundreds of light-years across. The Orion Nebula, visible to the naked eye as a fuzzy patch in the Sword of Orion, is a stellar nursery where thousands of stars are currently forming. It's one of the most studied objects in the sky, a laboratory where we can watch star formation happening in real time. Fact 70. Reflection. Nebulae don't emit their own light. Instead, they reflect and scatter light from nearby stars. These nebulae typically appear blue because the dust particles scatter blue light more efficiently than red light, the same reason Earth's sky appears blue. The most famous reflection nebulae surround the Pleiades, a young star cluster visible in the constellation Taurus. The stars of the Pleiades are moving through a dust cloud, and their light illuminates the material around them, creating delicate blue wisps visible in long-exposure photographs. These nebulae are transient phenomena. The stars are moving through the dust, not gravitationally bound to it. In a few million years, the Pleiades will have passed through the cloud, and the nebulae will fade as the stars move on. Fact 71. Planetary nebulae are some of the most beautiful objects in the universe. Despite their misleading name, they have nothing to do with planets. They are the glowing shells of gas ejected by dying stars like our Sun. The central star, now a hot white dwarf, illuminates the expanding shell with ultraviolet radiation, causing it to glow with colours that depend on the elements present. Many planetary nebulae have intricate structures, including rings, jets, and symmetrical lobes. These shapes are created by stellar winds, magnetic fields, and the presence of companion stars. The Cat's Eye Nebula shows concentric shells created by periodic ejections of material. The Helix Nebula looks like a giant eye staring back at us from space. The Ring Nebula is a favourite target for amateur astronomers, a perfect smoke ring expanding through space. Each planetary nebula is unique, a final artistic statement from a dying star, beautiful and doomed to fade. Fact 72. The lifespan of a planetary nebula is brief compared to the star's lifetime. The shell expands at tens of kilometers per second, and over tens of thousands of years, it gradually disperses into the interstellar medium. The central white dwarf continues to shine, but as it cools, its ultraviolet output decreases and the nebula fades. Eventually, the nebula becomes too diffuse and too faintly lit to be visible, and the white dwarf is left alone. A solitary ember drifting through space. The material ejected into the nebula doesn't disappear. It mixes with the interstellar medium, enriching it with helium, carbon, nitrogen, and other elements produced during the star's lifetime. That enriched material will eventually be incorporated into new stars and planets, continuing the cycle of stellar birth and death that has been ongoing for billions of years. Fact 73. Stars are not uniformly distributed through the galaxy. They concentrate in spiral arms, the great sweeping structures that give spiral galaxies their characteristic appearance. These arms are not permanent features, despite their solid appearance in photographs. They're actually density waves, regions where stars and gas temporarily bunch up as they orbit the galactic center. Imagine traffic on a circular highway. Sometimes cars bunch up in slow-moving clusters, even though individual cars are constantly entering and leaving those clusters. Spiral arms work similarly. Stars and gas clouds move through the arms as they orbit the galaxy, spending some time in the dense arm environment before emerging on the other side. Star formation happens more frequently in spiral arms because the gas is compressed there. Young, bright stars light up the arms, making them stand out. But older stars exist throughout the galaxy, in the arms and in the spaces between them. Fact 74. Our solar system is currently between spiral arms, in a region called the local spur or Orion arm. We're not in one of the galaxy's major spiral arms, but rather in a minor feature connecting larger arms. This location has advantages for life. Spiral arms contain more massive stars, which means more supernovae. If we lived deep inside a major spiral arm, we might be exposed to more frequent nearby supernovae, which could threaten life through radiation. Our position between arms gives us a quieter neighborhood, with fewer catastrophic events in our immediate vicinity. We orbit the galactic center once every 230 million years or so, a journey called a cosmic year or galactic year. The last time Earth was in this position, dinosaurs had not yet evolved. The next time we complete an orbit, who knows what life, if any, will exist on Earth to mark the occasion. Fact 75. Stars also move vertically, bobbing up and down as they orbit the galaxy. The galaxy has a disk shape, with most stars confined to a relatively thin layer. But the disk isn't rigid. Stars oscillate above and below the midplane as they orbit, like horses on a carousel moving up and down as they go around. Our Sun oscillates with a period of about 60 million years, moving a few hundred light-years above the galactic plane, then crossing through the midplane and moving a few hundred light-years below it, then crossing back. Some scientists have speculated that mass extinctions on Earth might correlate with our passages through the galactic plane, where we might encounter more dust and gas, or be exposed to different radiation environments. The evidence for this is weak and controversial, but it's an intriguing idea that our motion through the galaxy might influence the history of life on our planet. Fact 76. Sometimes when we look up at the night sky, we forget that everything out there is temporary. Every single point of light has a beginning and an ending. The stars we see tonight are not the same stars that will shine a billion years from now. The universe is constantly changing, constantly creating and destroying, and stars are right at the heart of that endless dance. When a massive star dies in a supernova, it doesn't just disappear into nothing. It sends a shockwave racing through space at thousands of kilometers per second, carrying with it all the energy and material from the explosion. That shockwave slams into nearby clouds of gas and dust, and when it does, it compresses them. It squeezes them tight. And sometimes, that pressure is exactly what's needed to start the birth of new stars. So death becomes birth. One star's ending triggers another star's beginning. It's a cycle that has been going on for billions of years, and it will continue for billions more. God's universe never stops renewing itself. He keeps transforming what was into what will be. Fact 77. There are stars out there that died long before humans ever existed, and yet we're still seeing their light right now. Light takes time to travel, and space is so incredibly vast that sometimes the light from a distant star takes thousands or even millions of years to reach us. So when you look up and see a faint star twinkling in the distance, you might be looking at something that no longer exists. You might be seeing a ghost. The star itself might have already run out of fuel, collapsed, exploded and faded into darkness. But its light is still travelling toward us, carrying the memory of what it once was. Every photon that reaches your eye left that star when it was still alive, still burning, still shining. In a way, stars never truly die as long as their light is still journeying through the universe. Their memory travels across space and time, reaching us long after they're gone. When you see that light, you're witnessing history. You're seeing the past preserved in a beam of radiation that has crossed unimaginable distances just to reach your eyes tonight. Fact 78. Our sun is middle-aged right now. It's about 4.5 billion years old, and it has another 5 billion years or so left before it runs out of hydrogen in its core. That might sound like forever, but in cosmic terms it's just a single chapter in a much longer story. Right now our sun is stable. It's fusing hydrogen into helium, releasing energy, keeping us warm and alive. But one day that will change. One day the hydrogen will run out and the sun will begin to swell. It will become a red giant, growing so large that it might swallow Mercury and Venus. Earth might survive on the outer edge of the sun's expansion, but it will be scorched and lifeless, stripped of its atmosphere and oceans. And then, after a few million years as a red giant, the sun will shed its outer layers in beautiful glowing shells of gas, creating what astronomers call a planetary nebula. That nebula will drift away into space, and all that will remain is a small, dense core, a white dwarf. That tiny ember will slowly cool over trillions of years, fading into the darkness. But we won't be here to see it. Humanity will either be long gone or living somewhere far beyond this solar system, looking back at where we came from with distant memories. Fact 79. When a white dwarf cools down completely, it becomes something called a black dwarf. But here's the thing. The universe is not old enough yet for any black dwarfs to exist. Even the oldest white dwarfs in the universe are still glowing faintly. They're still warm. It takes an unimaginably long time for a white dwarf to cool all the way down, much longer than the current age of the universe, which is about 13.8 billion years. So black dwarfs are theoretical. They're something that will exist one day, trillions of years in the future, when the universe is cold and dark and most of the stars have burned out. They'll be the final remnants of stars like our sun, cold and invisible, drifting through the emptiness. They won't emit any light or heat. They'll just be chunks of dense matter, floating silently through a universe that has grown old and quiet. In some ways, black dwarfs represent the ultimate fate of most ordinary stars, the final stage of a journey that began in fire and ends in stillness. Fact 80. Neutron stars are some of the strangest objects in the entire universe. When a massive star explodes in a supernova, sometimes the core that's left behind gets crushed down into something incredibly small and incredibly dense. A neutron star is only about 20 kilometers across, about the size of a city, but it contains more mass than our entire sun. That means a teaspoon of neutron star material would weigh about 1 billion tons. If you could somehow bring that teaspoon to Earth, it would instantly sink through the ground and keep going because nothing on our planet could hold it up. Neutron stars are so dense that their gravity warps space and time around them. They're almost like mini black holes, but not quite. The gravity on the surface of a neutron star is about 200 billion times stronger than gravity on Earth. If you tried to stand on a neutron star, you'd be flattened instantly into a layer of atoms just a few atoms thick. The escape velocity from a neutron star's surface is about half the speed of light, which means you'd need to be travelling at 150,000 kilometers per second just to break free from its gravitational pull. Fact 81. Some neutron stars spin incredibly fast. These are called pulsars, and they can rotate hundreds of times per second. Imagine something with more mass than the sun, spinning around faster than a helicopter blade. It sounds impossible, but it's real. Pulsars spin so fast because of something called conservation of angular momentum. When the core of a star collapses, it shrinks down dramatically, and just like a figure skater pulling in their arms to spin faster, the collapsing core speeds up. Some pulsars are so precise in their rotation that they rival the best atomic clocks we have on Earth. Astronomers can measure their pulses and predict exactly when the next one will arrive, sometimes down to the millisecond. They're like cosmic lighthouses, sweeping beams of radiation across space with perfect regularity. When those beams point toward Earth, we detect them as pulses, which is why they're called pulsars. The fastest known pulsar rotates 716 times per second. That's 716 complete rotations every single second. It's hard to even imagine something that massive spinning that quickly without tearing itself apart. Fact 82. Black holes are the final stage for the most massive stars. When a star is heavy enough, usually more than 20 or 30 times the mass of our sun, nothing can stop its collapse. Not even neutron degeneracy pressure. The core keeps collapsing and collapsing until it becomes a point of infinite density, something we call a singularity. Around that singularity, there's a boundary called the event horizon. If anything crosses the event horizon, even light, it can never escape. That's why black holes are black. They don't emit light. They don't reflect light. They're just empty voids in space where gravity is so strong that it breaks the rules we're used to. The event horizon isn't a physical surface. It's just a mathematical boundary, a point of no return. Once you cross it, all paths through space and time lead inward toward the singularity. There's no way out, no escape. No matter how fast you travel or which direction you point yourself, you'll always end up falling deeper into the black hole. Fact 83. But black holes aren't cosmic vacuum cleaners. They don't roam around space sucking everything in like some kind of gravitational monster. If our sun suddenly turned into a black hole right now, which it won't because it's not massive enough, Earth would keep orbiting exactly as it does now. The gravity would be the same. The only difference would be that we'd lose the light and heat, and everything would freeze. Black holes only pull things in if they get too close, just like any other massive object. The difference is that once you cross the event horizon, there's no coming back. You're gone forever. But as long as you stay outside the event horizon, you can orbit a black hole just like you'd orbit a star. In fact, there are stars that orbit close to the supermassive black hole at the center of our galaxy, whipping around it at incredible speeds, and they're perfectly safe because they're still outside the event horizon. Fact 84. Time behaves strangely near a black hole. Because gravity warps space and time, clocks tick slower the closer you get to the event horizon. If you watched someone fall into a black hole from a safe distance, you'd see them moving slower and slower as they approach the edge. Eventually, they'd appear to freeze in place, hovering just above the event horizon forever, their image getting dimmer and redder as time stretched out infinitely. But from their perspective, they'd cross the horizon in a finite amount of time and keep falling. They wouldn't notice anything special happening at the event horizon itself. They'd just keep falling inward toward the singularity. It's one of the strangest predictions of Einstein's theory of general relativity, and it's been confirmed through observations and calculations. Time is not absolute. It flows differently depending on where you are, and how fast you're moving and how strong the gravity around you is. Fact 85. Some black holes are supermassive. These aren't formed from dying stars. Instead, they sit at the centers of galaxies and contain millions or even billions of times the mass of our sun. Nobody knows exactly how they formed. Maybe they grew slowly over time, gobbling up stars and gas. Maybe they formed in the early universe when conditions were different and massive clouds of gas could collapse directly into black holes without forming stars first. Or maybe both. The black hole at the center of our Milky Way galaxy is called Sagittarius, a star, and it's about 4 million times more massive than the Sun. It's quiet right now, not actively feeding on much material, but sometimes it flares up and releases bursts of radiation. Astronomers have watched stars orbit around it, tracing elliptical paths that prove there's an enormous mass concentrated in a tiny region of space. One star called S2 completes an orbit around Sagittarius A star every 16 years, reaching speeds of up to 5,000 kilometers per second at its closest approach. Fact 86. When black holes feed, they create some of the brightest objects in the universe. As gas and dust spiral into a black hole, they heat up to millions of degrees and emit intense radiation. This glowing disk of material is called an accretion disk, and it can shine brighter than an entire galaxy. The material in the accretion disk doesn't fall straight into the black hole. Instead, it spirals inward gradually, orbiting faster and faster as it gets closer. The friction between different layers of the disk generates enormous amounts of heat, and that heat causes the disk to glow. Sometimes, black holes also produce jets of material that shoot out from their poles at nearly the speed of light. These jets can extend for thousands of light years, punching through the surrounding gas and creating giant lobes of hot plasma. Astronomers call extremely bright feeding black holes quasars, and they were much more common in the early universe when there was more gas and dust available for black holes to consume. Today, most supermassive black holes are quiet, sleeping giants at the centers of galaxies. Fact 87. Even black holes can die in a way. Stephen Hawking predicted that black holes slowly evaporate over time through a process called Hawking radiation. Near the event horizon, pairs of particles and antiparticles can pop into existence due to quantum effects. Usually they annihilate each other almost immediately. But sometimes one of the particles falls into the black hole while the other escapes. When that happens, the black hole loses a tiny bit of mass. Over an unimaginably long time, much, much longer than the current age of the universe, a black hole can evaporate completely. Small black holes evaporate faster than large ones, but even the smallest black holes we know of would take trillions upon trillions of years to disappear. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros. It's a number so large that it's almost meaningless. The universe would be unrecognizable by then, cold and dark and empty, with all the stars burned out and all the galaxies dispersed. Fact 88. Stars are not evenly distributed throughout the universe. They clump together in galaxies, and galaxies clump together in clusters, and clusters form superclusters. There are voids in space, huge regions with very few galaxies at all, and then there are dense regions where galaxies crowd together. Our Milky Way is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy and a few dozen smaller galaxies. In about 4 billion years, the Milky Way and Andromeda will collide and merge together, creating a new, larger galaxy. When that happens, the stars themselves probably won't crash into each other because there's so much empty space between them. But the collision will trigger massive waves of star formation as gas clouds slam together and collapse. The night sky will look completely different from Earth, if Earth still exists by then. Andromeda will grow larger and larger in the sky over millions of years, eventually filling the entire view before the two galaxies merge into one. Fact 89. The light from the most distant stars we can see has been travelling for billions of years. When we look at those stars, we're not seeing them as they are now. We're seeing them as they were billions of years ago, when the universe was much younger. Some of those stars might not exist anymore. They might have already burned out and died, but their light is still travelling toward us, and we're only now receiving it. In a way, looking out into space is like looking back in time. The farther away something is, the older the light is that we're seeing. The most distant objects we can observe are so far away that we're seeing them as they were when the universe was just a few 100 million years old. We're watching the early stages of galaxy formation, seeing the first generations of stars being born. It's like having a time machine that lets us peek into the distant past. Fact 90. There are stars we will never see. The universe is expanding, and the farther away a galaxy is, the faster it's moving away from us. This is because space itself is expanding, carrying galaxies along with it. Some galaxies are so far away that their light is being stretched into wavelengths we can't detect, and some galaxies are moving away so fast that their light will never reach us, no matter how long we wait. There's a kind of horizon in the universe, a boundary beyond which we can never see. Those stars exist, but they're forever out of reach. As the universe continues to expand and accelerate, more and more galaxies will cross this horizon and disappear from view. Eventually, trillions of years in the future, all the galaxies outside our local group will have moved so far away that they'll be invisible. Future civilizations in that distant era might look up and see only their own galaxy in an otherwise empty sky, with no way to know that there were ever other galaxies out there. Fact 91. Stars are made of the same stuff we are. Every atom in your body, except for hydrogen, was forged inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood. All of it came from stars that lived and died billions of years ago. When those stars exploded, they scattered their atoms across space, and eventually those atoms came together to form new stars, new planets, and new life. You're literally made of stardust. It's not just a poetic idea. It's a scientific fact. We're all connected to the stars in the most fundamental way possible. The hydrogen in your body was created in the Big Bang, 13.8 billion years ago. But everything else, all the heavier elements, came from stars. Some came from red giants that gently puffed their outer layers into space. Some came from supernovas that exploded violently. And some came from neutron star collisions that created brief flashes of intense heat and pressure, forging the heaviest elements like gold and platinum. Fact 92. The study of stars is called stellar astronomy, and it's one of the oldest sciences in human history. People have been watching the stars for thousands of years, trying to understand what they are and how they work. Ancient civilizations used the stars to navigate, to keep track of time, to tell stories. They didn't know that stars were distant suns, or that they were powered by nuclear fusion, or that they lived and died over billions of years. But they looked up with wonder just like we do. And slowly, over centuries, we began to understand. We learned that stars are not eternal. We learned that they're born from clouds of gas, that they burn through nuclear reactions, that they change and evolve and eventually fade away. And we learned that the story of stars is also our story. The ancient Greeks thought stars were fixed points of light attached to a crystal sphere that rotated around the Earth. It wasn't until the Renaissance that astronomers like Copernicus and Galileo began to understand that Earth was not the centre of everything, and that the stars were much farther away than anyone had imagined. Fact 93. There are stars that pulsate, growing brighter and dimmer in regular cycles. These are called variable stars, and they come in many different types. Some pulsate because they're unstable, expanding and contracting like a beating heart. Others vary in brightness because they're actually two stars orbiting each other, and they eclipse one another as they go around. Astronomers use variable stars as tools to measure distances in the universe. Certain types of variable stars, like Cepheid variables, have a direct relationship between their brightness and their pulsation period. By measuring how fast they pulsate, astronomers can figure out how bright they truly are, and by comparing that to how bright they appear from Earth, they can calculate how far away they are. It's like having a cosmic ruler. This technique was used by Henrietta Leavitt in the early 20th century, and it revolutionized our understanding of the size of the universe. Edwin Hubble later used Cepheid variables to show that some of the fuzzy nebulas astronomers had been observing were actually entire galaxies far beyond the Milky Way. Fact 94. Some stars are so old that they were born when the universe was still young. These ancient stars are called population 3 stars, and they're made almost entirely of hydrogen and helium, with almost no heavier elements. That's because they formed before the first generation of stars had died and spread heavy elements throughout the universe. Astronomers have been searching for population 3 stars for years, but they haven't found one yet. They might all be gone by now, having burned out billions of years ago. Or maybe a few are still out there, hidden in the farthest reaches of space, waiting to be discovered. Finding a population 3 star would be like finding a fossil from the very beginning of cosmic history. It would tell us about the conditions in the early universe and help us understand how the first stars formed and evolved. Some astronomers think population 3 stars might have been much more massive than typical stars today, perhaps hundreds of times the mass of our Sun, and they would have lived fast and died young, exploding as supernovas after just a few million years. Fact 95. The colour of a star tells us a lot about it. Red stars are cooler, blue stars are hotter. It might seem backwards, because we usually think of red as hot and blue as cold, but in terms of temperature, blue flames are hotter than red flames. The same is true for stars. A red star might have a surface temperature of around 3,000 degrees Celsius, while a blue star might be 30,000 degrees or more. Our Sun is yellow-white, which means it's somewhere in the middle. Its surface temperature is about 5,500 degrees Celsius, and all of this information, the colour, the temperature, the brightness, helps astronomers understand what's happening inside the star and how long it has left to live. Astronomers classify stars based on their temperature and colour, using a system that goes from hottest to coolest. The categories are O, B, A, F, G, K and M. Students remember this sequence using the phrase, "Oh, be a fine girl, kiss me." O stars are blue and incredibly hot. M stars are red and relatively cool. Our Sun is a G-type star right in the middle of the sequence. Fact 96. When we talk about the death of a star, it can sound sad. But death is not an ending in the universe. It's a transformation. The atoms that made up the star don't disappear. They spread out into space and become part of new clouds, new stars, new planets, new life. Nothing is ever truly lost. Everything is recycled through the laws God established. His universe is constantly being renewed, broken down and built back up in new forms, and stars are at the heart of that process. They take simple hydrogen and helium and turn it into all the other elements. They live for millions or billions of years, shining light into the darkness, and when they die, they give their atoms back to the universe so the cycle can continue. This process of recycling has been going on for billions of years through countless generations of stars. Each generation enriches the universe with more heavy elements, making it possible for planets like Earth to form and for complex chemistry to develop. Without stellar death, there would be no carbon, no oxygen, no iron, no silicon. There would be no planets, no oceans, no life. Fact 97. Every star has its own story. Some are born alone, drifting quietly through space. Others are born in crowded clusters with thousands of siblings. Some live fast and die young, burning through their fuel in just a few million years. Others live slowly and quietly for tens of billions of years. Some die gently, fading away into white dwarfs. Others die violently, exploding in supernovas or collapsing into black holes. But all of them, every single one, plays a role in the grand story of the cosmos. They light up the darkness. They create the elements that make life possible. They shape galaxies and drive the evolution of the universe, and they remind us that we are part of something vast and ancient and ongoing. The nearest star to our Sun is called Proxima Centauri, and it's about 4.2 light-years away. That might not sound like much, but it means that light from Proxima Centauri takes 4.2 years to reach us. If we could somehow travel at the speed of a light, which we can't, it would still take over 4 years to get there. Space is vast beyond our ability to truly comprehend. The fastest spacecraft humans have ever built would take tens of thousands of years to reach even the nearest star, and there are billions upon billions of stars in our galaxy alone, each one potentially with its own planets, its own story. Some stars are so different from our Sun that they're almost alien. There are stars that are 1,000 times larger than our Sun, so big that if you put them where our Sun is, they would swallow up Mercury, Venus, Earth, Mars, and even Jupiter. There are stars so small and dim that they barely glow at all, red dwarfs that will burn for trillions of years, outlasting every other type of star in the universe. There are binary stars that orbit each other in a cosmic dance, sometimes so close that they exchange material, with gas flowing from one star to the other. There are stars that are part of triple or quadruple systems, orbiting each other in complex patterns that would make the sky from any planet in those systems look completely alien. If you lived on a planet orbiting a binary star, you might have two suns in the sky, casting double shadows, creating strange seasons as your planet moved around both stars. The diversity of stars is stunning. Each one is unique, with its own mass, its own temperature, its own brightness, its own lifespan, its own destiny. Fact 98. Looking up at the stars can make you feel small, and you are small compared to the scale of the universe. But you're also part of it. You're not separate from the cosmos. You're made from the same materials God spread through it. In a very real sense, you are creation reflecting on its creator. You are stardust that has learned to think, to feel, to wonder, and that's not small at all. That's extraordinary. Carl Sagan once said that we are a way for the cosmos to know itself. Through us, through our eyes and our minds and our instruments, the universe is able to observe itself, to study itself, to understand its own nature. Every time you look up at the night sky and feel that sense of wonder, you're participating in something profound. You're continuing a tradition that stretches back to the earliest humans who ever looked up and wondered what those points of light were. Ancient humans didn't understand what stars were, but they still felt that connection. They created myths and stories about the stars. They saw patterns in the sky and imagined heroes and animals. They used the stars to navigate across oceans and deserts. They tracked the movements of the stars to know when to plant crops and when to harvest. The stars were woven into the fabric of human culture long before we understood their true nature, and now we do understand. We know that stars are not just lights in the sky. We know they're massive spheres of plasma held together by gravity, powered by nuclear fusion, creating the very elements that make up our bodies and our world. We know that when we look at stars, we're looking back in time, seeing light that left those stars years or centuries or millennia ago. We know that we're made of star material, that the universe is inside us just as much as we're inside the universe. That knowledge doesn't diminish the wonder. If anything, it makes it deeper. When you understand what stars really are, when you grasp the incredible processes that power them and the vast scales of time and space involved, the wonder only grows. You realize that you're not just looking at distant lights, you're looking at the birthplaces of atoms, the engines of creation, the hearts of the cosmic story that includes you. Fact 99. The future of stars is tied to the future of the universe itself. Right now, we're living in what astronomers call the stelliferous era, the age of stars. This is the time when stars are abundant, when galaxies shine brightly, when the universe is full of light and energy. But this era won't last forever. Eventually, in trillions of years, all the hydrogen in the universe will be used up. No new stars will be born. The existing stars will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. The universe will grow darker and colder. Galaxies will fade. And eventually, the universe will enter what's called the degenerate era, when the only sources of light are the occasional flashes from colliding stellar remnants. After that comes the black hole era, when even the white dwarfs and neutron stars have decayed, and all that's left are black holes slowly evaporating through Hawking radiation. And finally, in the unimaginably distant future, comes the dark era, when even the black holes are gone and the universe is nothing but a thin soup of particles spread across infinite space. But that's so far in the future that it's almost meaningless to us now. For now, and for trillions of years to come, stars will continue to shine. The stelliferous era will last for about 100 trillion years. We're only 13.8 billion years into it. That means we're living in the very early stages of the age of stars. The universe is still young. Most of the stars that will ever exist haven't been born yet. Red dwarf stars, the smallest and longest-lived stars, will continue burning for 10 trillion years or more. Long after our sun has died, long after the Milky Way has merged with Andromeda, long after most of the bright blue giants have exploded and faded, red dwarfs will still be quietly glowing. They'll be the last stars to die, the final embers in a darkening universe. But even they will eventually run out of fuel. When the last star finally goes dark, the universe will enter a new phase, one without light, without heat, without the familiar glow of stars. It will be a strange and lonely place, but it will still be the same universe, still governed by the same laws of physics, still existing, still evolving in its own way. Some scientists wonder if new forms of structure and complexity might emerge in that far future, things we can't even imagine right now. Or perhaps the universe will simply fade into cold, dark emptiness. We don't know. We can't know. But we do know that right now, in this moment, we're living in the golden age of stars, when the universe is bright and alive and full of possibility. Fact 100. So tonight, as you drift off to sleep, remember that the stars are still out there. They're still being born in distant clouds of gas and dust. They're still burning bright, fusing atoms in their cores, releasing light that will travel across the universe for thousands or millions of years. They're still dying, exploding, collapsing, transforming. The universe is alive with light and energy and change, and you're part of that story. You always have been, you always will be. The atoms in your body have been on a journey that stretches back to the beginning of time. They were created in the Big Bang, forged in the cores of ancient stars, scattered across space in violent explosions, gathered together in clouds of gas and dust, incorporated into the disk of material that formed our solar system, and eventually assembled into the planets and the life that lives on them. You carry that entire history within you. Every breath you take, every thought you think, every beat of your heart is part of the ongoing story of creation. Rest well tonight, knowing that you are connected to something infinite and beautiful, something that began 13.8 billion years ago and will continue for trillions of years more. You are not separate from the stars. You are made of the same substance. You are animated by the same energy that powers them. In the most literal sense possible, you are a small part of creation that has become aware of its maker's signs. Hydrogen atoms formed in the Big Bang eventually found their way into a star. That star burned for millions of years, creating heavier elements. The star died and released those elements into space. Those elements drifted through the cosmos for eons, eventually becoming part of a cloud that collapsed to form our solar system. Some of those atoms ended up on Earth. Through billions of years of chemistry and evolution, those atoms became part of living things. They became part of you. And now, with your consciousness, those atoms can look back up at the stars and understand where they came from. You're not an accident or an afterthought. You are part of God's plan, part of His story, part of the great cosmic journey He set in motion. From simple hydrogen to living, thinking beings. And when you look up at the stars, you're closing a circle. You're connecting the beginning and the middle and the eventual end. You're bearing witness to the beauty and grandeur of it all. So rest now. Let your thoughts drift like clouds of stellar gas. Let your worries dissolve like a star shedding its outer layers. You are safe. You are stardust, and you are starlight, a small part of God's creation reflecting His design. And if you're still awake, maybe stay for the next chapter, but if not, that's okay too. The stars will still be there tomorrow night, and the night after that, and every night for as long as you want to look up and wonder. They've been there for billions of years before you were born, and they'll be there for billions of years after, and they will remain as long as God wills. Right now, in this moment, they're shining for you. Sleep well. Dream of distant suns and nebulas and galaxies spiraling through the void. Dream of the connections that bind everything together. Dream of the incredible journey that brought you here, and know that when you wake up, the universe will still be there, still turning, still creating, still telling its endless story, by God's command. Good night.